Fundamental Manufacturing Processes video series, examining the tools and techniques of precision metalworking. This program is an introduction to cutting tools and tool geometries for turning and milling. Cutting tools for metal cutting have many shapes, each of which is described by its angles or geometry. Every metal cutting tool shape has a specific purpose. Cutting efficiently requires using the right shaped tool for the task. If you try to carve a turkey with a butter knife, you'll most likely fail. This is also true with metal cutting, where the selection of cutting tools is considerably more demanding. The first goal in machining is to achieve the most efficient separation of chips from the metal workpiece. The edges of the cutting tool, driven by the power of the machine tool into the workpiece, forces grains of the metal to move away from the advancing cutting edge. This displacement causes the metal to fail. A chip forms along this line of failed metal, which separates from the work material. How that material failure and chip formation takes place is influenced by the work material, the tool geometry, the forces applied by the machine tool, and various conditions in the process, such as heat and vibration. An efficient cutting tool geometry is one that minimizes heat in the cut and achieves a cool, properly formed, manageable chip while cutting the given workpiece material. Using the wrong cutting tools for a given operation may cause the tool to not cut at all, wear the tool out too quickly, break the tool, damage a workpiece, or fail in other ways. Before final selection of a cutting tool can be made, certain process parameters must be known, such as the composition and hardness of the workpiece, its shape and surface condition, the machine's horsepower, the machine's feed and speed capability, and the rigidity and security of the work-holding method. All these variables factor into the selection of tool shape, tool material, and machining process parameters. Nearly all turning uses single-point cutting tools, that is, tools that cut in a single cutting edge. Most turning today is done with coated indexable carbide inserts, but the tool material may also be high-speed steel, brazed carbide, or inserts of ceramic, cubic boron nitride, or polycrystalline diamond. Several decisions are required when choosing tools for turning, including the selection of the material or grade, the geometry, and the tool holder design. Just a few basic geometries and carbide grades are used in 75% of turning applications. Tooling decisions for lathe operations, such as hole making, boring, threading, and parting off, require unique selections of grade, geometry, and tool holder. When turning with inserts, much of the required geometry, such as clearance angles, is built into the tool holder rather than the insert itself. But let's focus first on inserts. The geometry of an insert includes its shape, relief or clearance angle, tolerance, type, its inscribed circle or IC size, thickness, nose radius, and the insert's chip breaker design. For turning, insert shape selection is based on the trade-off between strength and versatility. The larger point angles are the strongest and most economical. Those include round inserts for contouring and square inserts for roughing and finishing. The smaller angles, such as the 35-degree diamond and the 55-degree diamond, provide the greatest versatility for intricate contouring. Trigon inserts have 6 cutting edges, yet have the strength of 80-degree diamonds, which have only 4 edges. Cost per edge is lower, so trigons are a popular turning insert shape for light to medium depths of cut. Inserts are molded or ground. Molded inserts are more economical and have wide application. Ground inserts are required when indexability must be held within close tolerances, or when well-defined or sharp cutting edges are needed. Several angles are important when introducing a cutting tool's cutting edge into a rotating workpiece. Those angles include The angle of inclination, which when viewed from the side or front, is the angle of the insert seat or pocket in the tool holder from front to back. The angle of inclination may be positive, negative, or neutral. The cutting tool's rake angle is the relation of its cutting edge to the cut itself, and may also be positive, negative, or neutral. The effective rake is a combination of the tool holder's angle of inclination and the rake built into the insert. The largest influence on chip flow in turning is the top or back rake angle. Viewed from the side of the tool holder, this is the angle created by the top of the cutting tool and an imaginary line drawn horizontally through the workpiece diameter. A positive top rake tool cuts freely, with reduced power requirements and reduced temperatures. A negative top rake tool is generally stronger, but it generates more force and requires more power. A negative or a neutral top rake is preferred for rough turning operations, particularly for cast iron. In addition to the angles built into an insert and a tool holder, the angle at which the primary cutting edge of the insert enters the workpiece, called the lead angle, is also important. The lead or entry angle is the angle between the direction of the cutting tool feed and the cutting edge. Sometimes the workpiece shape determines the lead angle. The lead angle also influences the variety of cuts that may be taken with that tool. The tool nose radius must be equal to or smaller than the smallest radius on the workpiece for cuts made with that tool. Other factors influencing tool nose radius selection include the surface finish requirements and the tool strength, with the largest tool nose radius permissible giving the greatest strength. The larger the tool nose radius and the stronger the corner, the greater is the cutting tool's ability to absorb heat and produce a smoother surface. However, a larger radius also generates greater radial cutting forces and runs the risk of vibration. The quality of the finished turn surface is mainly from a combination of the cutting tool's tool nose radius and the feed per revolution. Insert size is designated by the largest circle which can be inscribed within the perimeter of the insert, called the inscribed circle or IC. As the size of the insert increases, so does the insert's thickness. Insert size is directly connected to the tool holder selected. The pocket size of the tool holder and the inscribed circle size of the insert must be selected together. The holder pocket shape is determined by the shape of the insert. Insert size is selected according to the maximum depth of cut to be taken and the lead angle. This provides maximum cutting edge engagement. If the effective cutting edge length is less than the depth of cut, a larger insert should be selected or the depth of cut reduced. Light cuts can be done with a smaller insert, but too small an insert might require 2 passes to be made instead of 1, which is uneconomical. For even the smallest jobs, there are appropriately sized inserts, tool holders, and boring bars. Since a sharp edge is weak and fractures easily, an insert's cutting edge is prepared with particular shapes to strengthen it. Those shapes include a honed radius or rounding on the corner, a chamfer to break the edge, a land or small negative slope, or a combination of the 3. A fine finishing insert may need only a small edge rounding, while a heavy roughing insert may have a significant negative land for edge strength. The drawback of negative lands is that they need more power and alter chip formation unfavorably. Insert-type tool holders for turning are made of steel and consist of a shank, head, pocket, and clamping hardware. Tool holder pockets are machined to accurately locate and orient the insert. Sometimes a carbide seat is used between the pocket and the insert. Tool holders are also either left-handed, right-handed, or neutral. There is a wide selection of tool holders and boring bars. They are designated by the shank size, hand of the tool, method of clamping, insert shape, insert size, insert style, and rake angle. Tool makers have clamping systems for their various insert families. Roughing and finishing tools may have different clamping mechanisms or clamp configurations. The size and type of tool holder is determined by the turning operation, the feed direction, the size of the cuts, the machine tool design, the need for accessibility, and sometimes the shape of the workpiece, if, for example, contour turning is involved. Turning tool holder styles are defined by their lead angle and the shank offset. Longitudinal turning, facing, and various contour cutting operations require certain tool holder forms. There are hundreds of styles. In turning, a 15 to 30 degree reverse lead angle tool holder is often used. This style distributes the cutting stresses, thins the chip, and reduces pressure on the edge. When turning to a square shoulder, the tool holder should have a 0 degree lead angle or a -5 degree lead angle. In boring, a 0 degree lead angle is preferred, as it directs the feed force along the axis of the work, minimizing deflection. Some tool holders are designed for facing. The offset style tool holder lets work be performed closer to the chuck jaws and is generally chosen over the straight shank. Tool holders and boring bar should be positioned as far back in the turret or tool block as possible to maximize support. Overextended tools chatter and cause insert breakage. In turning, effectively breaking a chip is just as important as making the chip. A properly breaking chip contributes to an efficient process and a good finish on the workpiece. Badly controlled chips are a nuisance, a production bottleneck, and are potentially unsafe. Proper chip breaking results from a balance between the feed rate, depth of cut, and the chip breaker geometry in the cutting tool. The chip breaker groove is molded into the insert in a wide variety of proprietary designs. Grooves, bumps, waves, dimples, and all sorts of shapes have been designed into cutting tools. Chip breaker geometries are all designed to work at designated feed rates and depth of cut. High-pressure coolant effectively promotes chip breaking if all else fails. There are 4 basic chip types in turning. Chips that resemble small 6s or 9s are the ideal type of chip. They are easiest to dispose of and are made in turning when tools are cutting most efficiently. The helical chip is acceptable if small enough. The long stringy chip, sometimes called a hay chip, may snarl the work and become a safety hazard. The chip breaker, if one is present, is too wide and shallow. More chip breaking action is required and can be achieved by either selecting another insert design or by moving the chip breaker closer to the cutting edge or by increasing the feed rate. A corrugated chip is the opposite of a stringy chip. It is caused by the chip breaker being too narrow and deep, thus crowding the chip. This promotes excess cutting edge wear and rapid tool failure. A corrugated chip can be remedied by moving the chip breaker back or by selecting a different chip breaker design. In turning steel, chip color can indicate if the heat generated by the machining process is being transferred away sufficiently from the part and into the chip. A chip absorbing heat leaves a steel workpiece light gold in color, then turns blue. But if the chip immediately turns dark blue at the cutting edge, this suggests excessive heat is being generated. A multi-point tool has 2 or more chip-producing edges on a common body and is rotated to cut. Some examples of multi-point tools include face milling cutters, end mills, drills, reamers, and taps. Let's explore multi-point tools by focusing on face milling cutters. Face milling cutters effectively generate flat surfaces with the spindle perpendicular to the work surface. The cutter body has multiple pockets to accept a variety of indexable insert types. As the cutter rotates, each insert edge alternatively enters and leaves the cut, removing a small amount of material in a short, discontinuous chip. The chip thickness at the start of the cut is called the undeformed chip thickness. Most milling with indexable insert milling cutters is performed using the climb milling mode, with the insert biting into the thickest portion of the chip first and then thinning towards zero upon exit. This is the reverse of the conventional milling mode, in which the milling cutter bites into the minimum chip thickness at the start of the cut and exits at the maximum chip thickness. The milled surface results from the combined action of cutting edges located on the periphery and face of the cutter. The flat milled surface has no relation to the contour of the individual teeth, except when milling a shoulder. Not all face mills are used for large, straight cuts. Some small diameter face mills are used to ramp into a surface, then plunge to a depth, and interpolate outwards to mill a large pocket more efficiently than an end mill could. There are major variables in the design of face milling cutter bodies which must be considered when selecting tools. These include the cutter's diameter, the hand of cut, the cutter geometries, including rake and lead angles, the insert pocket design, the milling cutter pitch, and the cutter's mounting method. For cutting, the effective diameter is the most significant concern. The effective diameter is measured from the highest point on an insert on one side to the highest point on the insert on the opposite side. For proper positioning, the face milling cutter's effective diameter should be about 1.5 times the width of the cut desired. This allows 1/4 to 1/3 of the cutter to overhang the edges of the workpiece, providing optimal chip formation. If the diameter of the face milling cutter is the same as or barely larger than the width of the workpiece, then the chips generated will be too thin at the entry and exit of the cut. This results in a buildup of heat and friction, which will reduce tool life. The hand of the cutter is determined by examining the cutter's face while running on a machine tool. A right-hand cutter rotates counterclockwise, and a left-hand cutter rotates clockwise. Rake angles in milling cutters are determined by the cutter body and by the insert. Two rake angles, the radial rake and the axial rake, are determined by the position of the insert pockets in the cutter body. The radial rake is the angle measured between the insert face and a radial line drawn from the cutter axis to the cutting edge, hence the name radial rake. If the insert tilts toward the chip gullet, it has a positive radial rake. If the insert tilts away from the chip gullet, it has a negative radial rake. The axial rake is the angle measured between the insert face and an axial line or plane, and it may also be positive or negative. The combination of axial and radial rake angles yield 3 geometries of milling cutters: negative radial and axial, which offers the strongest edges but generate the greatest cutting forces; positive radial and axial, which provides the freest cutting; and negative radial, positive axial, which presents a strong edge to the work but pulls the chip up. The rake angle on the face milling cutter inserts, in conjunction with the cutter body's radial and axial rake angles, contributes to the cutter's effective rake. The cutter's lead angle influences cutting forces and chip thickness. The greater the lead angle, the greater the axial force, and the longer but thinner the chip. Standard milling cutters come in 0, 15, 30, and 45-degree lead angles. Most face mills are designed with insert pockets that are fixed. Other cutters are modular and accept a variety of interchangeable insert cartridges that hold various insert designs and seat the inserts at different angles. This allows the orientation of the inserts to be varied using the same cutter body. The pitch of a milling cutter is determined by the number of inserts in relation to the cutter diameter and can be defined as the distance from a point on one edge to the same point on the next edge. The coarser the pitch, the larger the chip gullet. Gullet size is important in face milling, since the chips are generally confined to the gullet until the insert exits the cut. Cutters may be coarse pitch, fine pitch, or extra fine pitch. Fine pitch cutters are used primarily for milling cast iron or for finishing work. Coarse pitch cutters provide a large gullet space necessary for milling ductile materials or in wide cuts. They are chosen for everyday work. Milling inserts are available with various grades and shapes. In addition, milling inserts have their own corner geometries, including the radius and the wiper flat. A large corner radius produces a finer finish than a small radius, but a corner wiper flat on the insert produces the finest surface finish. Sometimes a single wiper insert in a cutter will improve the surface finish, even if all the others are roughing inserts. For best surface finish and longest tool life, all inserts must be preset to carry an equal load. One or two inserts protruding further than the others will carry the cutting load and wear out prematurely. To hold close tolerances in milling, a very stable mounting is essential. There are several methods of mounting face milling cutters. Milling cutters under 3 inches in diameter are usually integral shank cutters. Face mills between 3 and 8 inches in diameter are mounted onto an adapter and go into the spindle. Face mills from 8 inches diameter and up may mount directly to the spindle. As an introduction, we've covered only a few of the many aspects of milling with carbide tools. Extensive calculations are also involved when choosing effective cutter types, cutter paths, and cutting parameters. Let's re-examine the material contained in this videotape. Cutting tools cut with an edge, and those edges can be described by their geometry. For metal cutting efficiency, it is critical to select the edge that cuts best, given the material and cutting conditions. The purpose of the edge and its geometry is to create a chip. The right geometry creates chips cleanly and efficiently. The wrong geometry may not cut at all, or cut poorly, fail prematurely, or damage the workpiece surface. Cutting tools fall into 2 broad classes: single point and multi-point tools. Turning uses single point cutting tools, usually coated indexable carbide inserts. Selecting turning inserts involves choices of insert grade, geometry, and tool holder design. The geometry of an insert includes its shape, relief or clearance angle, tolerance, type, its inscribed circle or IC size, thickness, nose radius, and the insert's chip breaker design. The largest influence on chip flow in turning is the top or back rake angle. This is the angle created by the top of the cutting tool and an imaginary line drawn horizontally through the workpiece diameter. A positive rake cuts freely. A negative rake is stronger but generates more force in cutting. The tool nose radius helps determine insert strength as well as workpiece surface finish. Insert size is designated by its inscribed circle, and the inscribed circle size of the insert must match the pocket size of the tool holder. In turning, making a chip is only half the battle. The other half is effectively breaking the chip with the right chip breakers and operating parameters. Tool holders and boring bars may be designated by their shank size, hand of the tool, method of clamping, insert shape, insert size, insert style, and rake angle. Multi-point tools rotate to cut. Face milling cutters are a type of multi-point tool. Face milling cutters vary in diameter, hand of cut, geometry, pitch, insert pocket design, and mounting method. The 2 rake angles determined by face milling cutter bodies are the radial rake and the axial rake. These 2 may combine in 3 ways for 3 different geometries of face mills. negative radial and axial, positive radial and axial, and negative radial, positive axial. Face mills may be coarse pitch, fine pitch, or extra fine pitch, depending on the number of inserts relative to the tool's diameter. The coarser the pitch, the larger the gullet size. Milling inserts with a large corner radius or a wiper flat provide a fine surface finish.